Hey everyone, it's Mr. Glover here. Just about to do our next video lesson. So the topic today is on properties of quadratic functions. Up until this point, we've spent a lot of time focusing on the equations, so a quadratic equation. Today we're going to define quadratic functions. We're going to graph some of them, take a look at some properties of them, and we'll learn sort of what to look for when graphing a quadratic function. So recall the definition of a quadratic equation. It's a polynomial that could be written in the form of ax squared plus bx plus c equals 0. That's how we define a quadratic equation. In this case, it's going to have a degree of 2 because our highest power of x is 2. Any function that can be written in the form of y equals ax squared plus bx plus c, where a, b, and c are in real numbers, is called a quadratic function. So they look almost the same. The difference is that a quadratic equation equals a number, like 0, while a quadratic function is just defined as y equals ax squared plus bx plus c. The difference is that this is going to lock us into one value, while this allows us to graph a range of values depending on what x is. This is also probably a good piece of information. This is called the general form of a quadratic equation. And you'll see some different names for it. I used to call this standard form, but there are different names for different versions of the equation. So we're going to start out by plotting some functions, and we're going to just use an XY table to do that. We'll do the first couple by hand, and then I'll kind of explain a few tricks you can use. First of all, when you're graphing any function, you want to pick your coordinates carefully. If you don't really know where you want to choose, I usually suggest picking something near the origin, so near the middle. If you start with -2, -1, 0, 1, and 2 for your x values, those kind of lock you into the middle, and that'll give you an idea of the shape of your function. Sometimes you have to add extra points in, but this is usually enough for most cases. So basically what we're going to do is we're going to take x and plug it into the equation. So this would be like y equals -2 squared. So we'll get a y value of 4. This is going to be -1 squared, which is going to be 1. This will be 0 squared, which is 0. This will be 1 squared, which is 1. And this will be 2 squared, which is 4. So if we go ahead and we graph this, we have the point -2 and 4, -1 and 1, 0, 0, 1 and 1, and 2 and 4. So we get this shape, almost like a U. And we can use a graphing calculator, or we could use Desmos to graph this as well. If we want to quickly check that we did it right, we can go into Desmos. We can graph y equals x squared, and this is what it's supposed to look like. All right, moving on. Let's graph another one. Let's graph -x squared. So we're going to pick the same points. So we're going to pick -2, -1, 0, 1, and 2. But this time, instead of just y equals x squared, it's y equals -x squared. So this would be y equals -2 squared, which will be -4. This one will be y equals -1 squared, which will be -1. This will be y equals -0 squared, which is 0. This will be y equals -1 squared, which is 1. And this, or sorry, -1. And this will be y equals 2, negative of 2 squared, which is 4, -4. So if we go to graph this, our points are similar, but it's now going to look like it's opening down instead of up. So at -2, we have -4. At -1, we have -1. 0 is 0. 1 and -1. and 2 and minus 4. And so we get this kind of shape to our parabola. We can go and confirm this by graphing it in Desmos, or a graphing calculator. So we can graph this. We want to graph negative x squared this time. And this is what the function looks like. All right, let's try a little bit more of a tricky one. X squared plus 2x plus 1. Now, you can go ahead and you can plug -2, -1, 0, 1, and 2 in for x. And I'll show you how to do that for the first one. This would be equal to -2 squared plus 2 times -2 plus 1. And that's going to work out to just 1. We could go ahead, we could do that for each of these, and that's always an option. But if you've got technology available, there are easier ways to do this. If you've got a graphing calculator, you can input the function under the y equals menu, and then instead of hitting graph, you could hit second and graph, and that opens up a table of values, and you can literally copy your numbers down. It is possible to do a Desmos as well. Let's see if I can remember how to do it. Go over to Desmos. This is the function we're trying to graph. If we want a table of values, let's see here, graph. Maybe not. All right, I might have to double check this one. There is the other option, I guess, is to trace along. So you can trace from x value to x value. You can start at the bottom. This is -1 and 0. You could go over to x equals 0. You can then go over to x equals 1. You can go over to x equals 2. And it will literally tell you the y value. This is the y value of 9 would correspond to an x value of 2. So we can simply copy those values out. We don't have to plug them in every time. It's a good habit to get into when you're starting to learn how to do tables of values. But once you've done enough of them, you don't have to actually plug all your numbers in every time, unless you're stuck without a graphing calculator. Sometimes on a test you might be. Anyways, in this case, -1 will correspond to a y value of 0. 0 will correspond to a y value of 1. 1 will correspond to a y value of 4, and 2 will correspond to a y value of 9. So if we go to plot this, it's similar, but it's a little bit different. -2 and 1, -1 and 0, 0 and 1, 1 and 4, and 2 and 9. And it's going to be up here. So we can go ahead and graph this now. Now, technically, there are points past this on the left-hand side. We aren't just going to stop at a little check mark shape. If we had gone further to the left, we could have gone to a point of -3, and we would have had a y value up here. So technically, the graph does continue up. So it looks similar, but it's a little bit different in that it's been shifted over to the left. We'll do one more of these. So y equals -x squared plus 2. Again, we'll pick the same points. -2, -1, 0, 1, and 2 are going to be my x values. I can plug these into the equation, or I can use a graphing calculator, or I can use Desmos to tell me my y values. So -2 corresponds to a y value of -2. -1 corresponds to a y value of 1. 0 corresponds to a y value of 2. 1 becomes 1, and 2 becomes -2. So if we go to graph this, -2 and -2 is our first point. -1 and 1 is our second point. 0 and 2 is the third point. 1 and 1 is the fourth point. And 2 and -2 is the fifth point. So we end up with a parabola that opens down, but it's also been shifted up. Doesn't start at 0 anymore. And we can go ahead, we can graph this in Desmos. We can go down to this one, and we can make sure that we actually graphed it properly. And it's a good habit to get into, especially if you've got extra time. Double check your work, graph it on a graphing calculator. It only takes a minute. All right, so let's talk about some properties of quadratic functions. Shapes of these graphs all look similar. And there is actually a specific name. The shape itself is called a parabola. And that parabolic shape is the, it's kind of the curved, pointed shape. It's gonna come up a lot in nature. For example, anytime you throw an object up, it's going to follow a parabolic path up to its peak and then down to the ground. And you do see parabolas quite often in physics. The highest, lowest point of the graph has a special name. It's called the vertex. And the vertex is something that, for now, is going to be found graphically. There is a technique for finding it by hand. But we're going to be graphing them to find the vertex for now. If you draw a vertical line down the middle of the parabola, you will see identical halves. This line is called the axis of symmetry. So for example, if I was to draw a dotted line down the middle of my parabola, and I actually drew a decent parabola, this is called the axis of symmetry because the left side and the right side are reflections of one another. All parabolas will have one of these. The leading coefficient. So the leading coefficient, remember, that's the first number being multiplied by the highest power of x. This tells us information about what's called the orientation of the graph. And now that's whether it's upright or upside down. If you go through these graphs we just did, x squared is a positive leading coefficient, it opens up. Negative x squared has a negative leading coefficient, it opens down. Positive x squared opens up, but negative x squared opens down. So this tells us whether the function opens up or opens down. And a couple other facts are characteristics of our graphs. The y-intercept is always going to be the same as the constant in your equation. So for example, y equals x squared plus 3x minus 7. This one is going to have a y-intercept at negative 7. And the reason for that is the y-intercept is the point where x equals 0. It's the point along the y-axis. If x equals 0, every term except the constant gets eliminated. The x-intercepts are the roots of the corresponding quadratic equation. Now, this is the big idea. This is the thing that we'll spend time on throughout this chapter. And basically, by solving the equation, 0 equals x squared plus 4x plus 3, we've gone and plugged in a y value of 0. That's the x-intercept. We can now use algebra to find out the x-intercepts of our graph. This thing will factor into x plus 1 and x plus 3, which means that the solutions, or the x-intercepts, are going to be at the points x equals negative 1 or x equals negative 3. And that's kind of the tie-in between the equations and the graph of a function. We will spend more time on this later on in this unit. So this is a bit of a tricky one. It wasn't on your own, but we'll do it together. We're going to graph the function. We are going to create a table of values for the function. And we're going to find all of these characteristics, the x and y intercepts, the coordinates of the vertex, the equation of this axis of symmetry, and the domain and range of the function. The first thing we're going to do, though, is we're going to actually build our table of values. You could do this by substituting values into the equation, or you could do this by graphing it and creating a table of values using technology. Um, in light of time, I think I will tell you what the values work out to, but you can solve or you can create your y values however you see fit. I'm going to pick -3, -2, -1, 0, 1, 2, and 3, because that gives me a look at the origin or close to the middle of my graph. These points are going to correspond with y equals 20 when x equals -3. And again, that would come from plugging -3 in for x in our equation. -2 is going to correspond to 24. -1 will correspond to 24. 0 corresponds to 20. 1 corresponds to 12. 2 corresponds to 0. And 3 corresponds to -16. Okay. So if we want to graph this, we're going to have to kind of change the scale of our graph, because we've only got 1, 2, 3, 4, 5, 6, 7 squares, and we need to get up to 24. So we've got a few options here how we want to do it. We could make every y value worth 3, and then we're counting by 3s instead of counting by 1s. We could also make all our y values 5. Let's make them all 3. So it'll go up 3, 6, 9, 12, 14, 16, 18, or sorry, 12, 15, 18, 21, 24. That way the top point is going to be 24. We don't have to do it this way, but it's an option. And I guess we'll go 3, 6, 9. So if we want to graph this, x is -3 and y equals 20. X is -3, y equals 9, 12, 15, 18, 20 will be right around here. Well, you know what? This is only going to go up to 21. So 24 will actually be above the graph. -2 and 24. We've got -1 and 24. We've got 0 and 20. And actually, these points, 20 is actually close to the top, so 20 will be about here. 1 and 12. 2 and 0. And 3 and -16. So 3 and 3, 6, 9, 12, 15, 16. Sort parabola, again, it'll continue off to the left, just like it did on the right. And I also know that there is a point between these two. There should be a maximum somewhere up here. So the graph of this function looks something like this. Now, we've got to answer some questions about it. We need to find the x and y intercepts, the coordinates of the vertex, the equation of the axis of symmetry, the domain and range of the function. So we've got quite a bit to do here. Maybe we'll answer these down here. So question 1A was the x-intercept, or the x and y-intercept. X-intercept and y-intercept. Now you can do these by hand. The y-intercept I know is the constant, so the y-intercept should be 20. And we know that because it crosses at 20. So the y-intercept, y equals 20. The x-intercept, we could try and factor the equation and find it by hand, but we've got graphing technology. We may as well use graphing technology. So we can graph the function. And again, it does look like the graph we made. And we just need to go ahead and we need to find the x-intercepts. On a graphing calculator, it's a little bit trickier. You have to go to the trace menu, and then you have to calculate a 0. But in Desmos, it's simple. You just click on 0. -5 is our first x-intercept, and 2 is our second. So x equals -5 is 1, and x equals 2 is the other. Question B, coordinates of the vertex. Now, the vertex, we could turn our equation into vertex form, but We haven't really learned how to do that yet. On the graphing calculator, we just go to the vertex and we find it. Vertex occurs when x is minus 1.5 and y is 24.5. So the equation of our vertex is at minus 1.5 for x and a y value of 24.5 for y. And those brackets just tells me that's a point. So I basically defined a point, 1.5, minus 1.5, 24.5. That is this vertex here. Question C, find the domain, or sorry, the axis of symmetry. And here's the neat thing. With a parabola, the axis of symmetry lines up with the vertex. So if I were to draw a dotted line from the vertex down, that becomes the axis of symmetry. So when you're defining the axis of symmetry, you just need to know what coordinate the x coordinate of your vertex is. If we have a vertex at negative 1.5, well, that means the axis of symmetry is also at that point. So the axis of symmetry is at the point x equals negative 1.5. Technically, it's not a point, it's a line. It's all of the y values across this one x value. But once you know the vertex, you've got the axis of symmetry. Last but not least, D, the domain and the range of the function. Domain and range. So you can find these graphically. The domain is going to be caused by any restrictions in the x values. So there's only a few rules we can't break. We're not allowed negative square roots, and we're not allowed zeros on the denominator of a fraction. Anything else is fair game. So if we look at our equation, we're not breaking any of those rules with x. So we're allowed to put any x value into this equation, and it will spit out a y value with no errors. Because of that, my domain is that x is all real numbers. X is in the reals. Our range, though, there is a cap on our range. This is the highest value you're going to get out of the function. You won't get past x equal or y equals 24.5. Everything else is less than that. So the range is basically asking what are the possible y values? Well, the y values are that y is less than or equal to 24.5. And this is something you're going to have to graph it to find. All right, so one more concept today. It's called the first difference. And now this is a technique you can use to tell whether a table of values is a table for a quadratic function or whether it's a table for a linear function or some other kind of function. And it's a little bit of a trick because then we don't have to actually graph it to know. So the first difference, it's created by subtracting consecutive y values. So consecutive y values can be subtracted to find the first difference. And to go through this concept, we're going to find the first difference for a specific function. So the function is x squared plus 4x minus 6. And we need to create a table of values for this function. Most of the time in a question, you'll be given the table, but we need to make our own table this time. So again, we'll pick the same x values, minus 3, minus 2, minus 1, 0, 1, 2, and 3. Unless you've got a reason to move different x values, like if you know it's been shifted to the right, these are always a good starting point. If you plug minus 3 in for x, you will get minus 9 as your y value. Minus 2 gives a y value of minus 10. Minus 1 gives a y value of minus 9. 0, minus 6, 1, minus 1, 2, 6, and 3, 15. And now these are not something you're going to get really quickly. I'm just reading them out to you to try to save on a bit of time. You're going to get these by plugging x equals minus 3 into this equation or by creating a table of values on a calculator. So for the first difference, you won't have one for the very first point because there's nothing to subtract. So we can kind of cross it off or we can write not applicable. The second one, though, the idea is you take your existing y value and you subtract the previous one. So this first difference would be minus 10 minus negative 9. which is kind of like minus 10 plus 9, which gets us first difference of minus 1. The next first difference will be minus 9 minus negative 10, which is like minus 9 plus 10, which gets us a first difference of positive 1. Minus 6 minus negative 9 is our next first difference, which is like negative 6 plus 9, which is a first difference of 3. Minus 1 minus negative 6 gets us a first difference of 5. 6 minus negative 1 gets us a first difference of 7. And 15 minus 6 gets us a first difference of 9. So now we've got these pattern of numbers here. And you might notice that there's a relationship between every number. Minus 1 is 2 away from 1. 1 is 2 away from 3. 3 is 2 away from 5. 5 is 2 away from 7, and 7 is 2 away from 9. So basically, we're counting up by 2 each time. So we can say, let's try that again. We can say that the first difference increases by 2 each time. That tells me right away that this is a quadratic function. If we had a linear function and we did the first difference, we would find that the first difference is the same for every single one of these numbers. It would be the slope of our line. In a parabola, because you're not increasing at a constant rate, you're not going from 1 to 3 and 3 to 5, you're going from minus 9 to minus 10 and then down to minus 9 and then to minus 6. You're not getting constant change. You will get a difference in your first difference. So the pattern of first differences represent what's called an arithmetic sequence. This is something you'll learn about in grade 12 with sequences in series. It used to be a topic in grade 11, but it has been shifted up. The example is that each difference increases or decreases by a constant number. We go from minus 1 to 1 to 2 or to 3 to 5 to 7. It's like adding 2 each time. It's a sequence of numbers where everything is increasing by 2. This is true for all quadratic functions with a leading coefficient of 1. So essentially, the idea here, and I'll put it with a star, is that we use the first difference to determine whether a table of values is for a quadratic function. If the first differences are the same, if all first differences are equal, that tells me this is not a quadratic, this is a linear function. If all the first differences are increasing or decreasing, so if they increase or decrease by a constant, that tells me that it's a quadratic. So it's just a tool you can use to avoid some steps. You don't have to actually graph the function to tell whether it's quadratic. So that's where we'll end things today. We've gone through quite a lot today. There's quite a bit of material in these notes. So spend some time reading through them again and just double checking everything. I've got some questions for you. This is going to be your assignment for the next few days. We will talk about this a little more tomorrow when we have our Zoom meeting, but I think I'll end the video for now. So have a great rest of your day, everyone, and I will see you all tomorrow. Bye for now.